Section 4.3 is about how to divide one polynomial by another. And if we're going to kind of work through this from the easiest situation to the hardest, the easiest would be if you're dividing by a monomial. Because if you're dividing by a monomial, then you can break up the division or the quotient into simpler expressions, and then basically it's a bunch of law of exponents applications and you're done. And then, well, maybe you have to like rewrite with positive exponents or something, but basically you're done. So that's exactly what this is, where you can break it up into simpler expressions. And look at what I do here, where in this example, I start off where I've got this 4-term polynomial divided by a monomial. And basically what I do is I just break that up into pieces. So what that is it's this idea. Like if you had, I don't know, like 3 plus 8 over 16, you could write that as 3 over 16 plus 8 over 16, which I suppose is 1/2. But usually you would do this in the opposite direction, right? In order to simplify things, you would add the two fractions together and go, oh, that's 11 over 16. It's that idea just in the opposite order, right? Instead of having one expression, you break it up into a whole bunch. Because if you break it up into a whole bunch, these are relatively easy to simplify over here. Because then with the coefficients, all you have to do is divide. And then with the exponents, where you've got x raised to those powers, you can just subtract the exponents because you're dividing. There's the law of exponents part. So once you've got it broken up, so here it's this whole thing over 4x squared, and then I just wrote it as first term over 4x squared, then second, third, and fourth. And then the pluses and minuses show up in between the individual quotients in the same spots they show up in the original polynomial. Right, you got a plus here, then a minus, then a plus, just like over here you got a plus, minus, plus. And then once you've got this broken up into little quotients, then you can say, oh, well, 8 divided by 4, that's 2. And then x to the 4th over x squared, if you subtract the exponents, 4 minus 2 is 2. Right, and then you go to the next one, 12 over 4 is 3. Then with the exponents, you got 3 minus 2, which is 1. Third one, 24 over 4 is 6. 2 minus 2 is 0. And then the last one, 4 over 4 is 1, which I didn't write in. And then with the exponents, it's 1 minus 2, which would be negative 1. And then I just cleaned it up a little and then rewrote with the positive exponent down here. So like the 3x to the first, you would usually write as 3x. And the x to the 0 is just 1, so you just write that third term as a minus 6. And then the last one, in order to get a positive exponent, you bring that x to the negative 1 down, and it's 1 over x to the first, or just 1 over x. That's pretty much the whole idea if you're dividing by a monomial. So these examples here, I'm going to do the exact same thing. Like here with number 1, I'm going to write that as 3 separate quotients where the 5x to the 5th is in the denominator in each one. So I'm going to have 15x to the 6th over 5x to the 5th minus 25x to the 5th over 5x to the 5th minus 20x to the 4th over 5x to the 5th. And then we're basically going to do the same thing. We're then 15 over 5 is 3, and then x to the 6th on top, x to the 5th on the bottom, so 6 minus 5 is 1, and you would just have 3x, or I guess I can write that as 3x to the first. And then minus 25 over 5 is 5, and then those are going to, either you could say that they're going to cancel out, which then you're just left with a 5 right away, or if you subtract the exponents, I suppose you have x to the 0. So I'll write it with the x to the 0 for now, but it'll just be a minus 5 in the next line. And then minus 20 over 5 is 4. And then with subtracting exponents, 4 minus 5 is negative 1, so x to the negative 1. All right, so 3x to the first is just 3x. In the middle, you got a minus 5, and then minus 4 over x. And there we go, right? That is our quotient when we divide by that monomial of 5x to the 5th. All right, well then number 2 is the same idea. It's just that there are multiple variables. You don't really do anything differently. Like procedurally, it's still, you're going to break that up into 3 pieces because there are 3 terms in the numerator. So 3 little quotients, and then you simplify the same way. You just have an extra variable to deal with, but it doesn't really end up being any harder. And it looks like it might be, but it's not. So we're going to do the same thing. So 9x cubed y to the 4th over 3x squared, or 3xy rather, plus 24xy squared over 3xy minus 3xy over 3xy. All right, so what are we going to do with this? Well, 9 divided by 3 is 3. And then if you subtract the exponents with the x's, you got a 3 on top and a 1 on the bottom. So 3 minus 1 is 2. We got an x squared. Then with the y's, we got a y to the 4th on top and a y to the 1st on the bottom. 4 minus 1 is 3. Next term, 24 over 3 is 8. Those x's are going to cancel, right? Either that or you can say it's x to the power of 1 minus 1, which is 0. And then you got a y squared on top, a y on the bottom, so you just have 8y. And then that last part's just going to be a minus 1, right? Because 3 over 3 is 1, and then these are all just going to cancel out. So what we're going to end up with is that. 3x squared y cubed plus 8y minus 1. All right. That's pretty much it if you're dividing a polynomial by a monomial. But now, what if you're not dividing by a monomial? What if what you're dividing by, so what's in the denominator here, or I guess to use the more proper terminology, what's your divisor? What if that has multiple terms? So if you're going to divide a polynomial by another polynomial, where here polynomial is being used kind of loosely to mean one that's not a monomial, because if it was a monomial, you do what we were just doing. So there are a couple of things you could do. You could do it with long division, or in certain cases you can use synthetic division, which we're going to talk about in a little bit. But if you're going to use long division, it looks pretty similar to long division with integers. Like if you divide kind of a big number by some other number. So I just stuck one in here just as kind of a reminder of what this looks like, and then to kind of point at it and go, look, when you do it with the polynomials, it looks like this. So if you're going to divide 47/17 by 15, and you're going to do it with long division, so 47/17, then 15 doesn't go into 4, but it goes into 47, right? 3 times, since 3 times 15 is 45. And then if we subtract, we're going to end up with a 2. Right? And then you bring down the 1, and 15 goes into 21 once. 1 times 15 is 15. Subtract, you get 6, bring down that 7, and 15 goes into 67 4 times, since 4 times 15 is 60. And then if you subtract, you get 7, and that's your remainder. So what we end up with for our solution here would be 314, and then there are a couple of ways you could write the remainder. Like sometimes you see it with like an R7, but I'm going to write it this way. So 314 and 7/15, right? That's the other way of writing it, where you'd say it's the remainder over the divisor, which here is 15. And the reason I'm writing it this way is because that's what it's going to look like when we do it with polynomials. So it'll look pretty similar to this. All right, so now let's see what this looks like if we were going to do it with polynomials. So it's similar, except that you also have to worry about like multiplying through with the variables too. So let's see, we're going to divide this long thing by 4x plus 3. So even the way that it's arranged looks kind of similar, right? You got your divisor out here on the left. You got the division sign where you're going to put your dividend underneath. So 8x cubed plus 2x squared plus 17x plus 15. And you kind of do the same thing, but you just look at the leading terms. So another thing with the division, if you're going to do long division, we didn't have to worry about it here because both of these polynomials were already in standard form. But if they're not in standard form, you want to put them in standard form. Otherwise, the division gets a lot more complex. So these are already set up, but if you had to do it, you would do that first. Because then really you just look at the leading terms. So the leading term underneath is the 8x cubed. The leading term out here is the 4x. So what we got to do is we got to figure out what we need to multiply 4x by to get 8x cubed. And the way that I think about it is I just think about it piece by piece, like coefficient, then x. So I go, all right, coefficients. What do I need to multiply 4 by to get 8? I need to multiply 4 by 2 to get 8, right? Then what do I have to multiply x by to get x cubed? Well, because of that law of exponents where you can add the exponents together, I need an x squared. Because x squared times x, if you add the exponents, 2 plus 1 is 3, right? So x squared up here. And then you're going to multiply 2x squared by this. So 2x squared times 4x would be 8x cubed. But then 2x squared times 3 is 6x squared. And then we're going to subtract this, right? So just like the long division up above, right? You subtract, and then 8x cubed minus 8x cubed, that's nothing, right? 0x cubed. But then 2x squared minus 6x squared would be minus 4x squared. And then you bring down the next term, so plus 17x, right? Just brought right down there. So bringing down that 17x is kind of like bringing down the next digit up here when we're just dividing two integers. But then what do you have to multiply by 4x to get negative 4x squared? Well, I guess coefficients first. You have to multiply 4 by negative 1 to get negative 4. So I guess I need a negative here. But then negative x, right? Negative 1x, which I guess I can write it that way. Or just negative x, because x times x will give you the x squared. So negative x times 4x is negative 4x squared. And then negative x times 3 is negative 3x. And then if we subtract that row, we're going to end up with 17 plus 3, right? Because it's minus a negative 3. So we're going to get 20x plus 15. If then I bring that 15 down. And then what do we have to multiply 4x by to get 20x? Well, we need a 5, right? Because 5 times 4 is 20. So plus 5. And 5 times 4x is 20x. 5 times 3 is 15. And I'm basically out of room, but you can see what happens. If I subtract here, I'm going to get 0. So there's no remainder, right? So that would mean that what we're ending up with for our solution, or here for our quotient, would be 2x squared minus x plus 5. Okay, well then we got another one in number 5, and you can probably guess what's going to happen here, because it looks like number 5 should be shorter because the degree is smaller of the dividend. Right here it's 2 and up here it was 3. It will be a little bit shorter. The thing that will make this one a little different though is it's going to have a remainder that's not 0. And so that's the thing we got to go through, is how do you actually write that out? All right, so if we do the division, so we set this up, we're going to divide 6x squared minus 13x minus 19 by x minus 3. And then, all right, so we're playing the same game, right? We got to figure out what do you need to multiply x by to get 6x squared. Well, just with the coefficients, what do you have to multiply 1 by to get 6? 6. And then what do you have to multiply x by to get x squared? We need another x, right? So 6x times x would give you 6x squared. But then 6x times negative 3 is negative 18x. And then if you subtract, 13 plus 18 is 5x. So you end up with 5x and then bringing down the minus 19. So you need a 5, right? Because 5 times x would give you the 5x. So 6x plus 5. But then we'll have 5x minus 15. And then when we subtract, negative 19 plus 15 is negative 4. All right, so then what we're going to end up with here, I guess you could either say this is your solution or it's the quotient and the remainder. So our quotient was 6x plus 5. And then if I scroll up for a second, just notice how we wrote the remainder here as 7 over 15. Because we ended up with the 7 left over and then divided by that divisor of 15. We're going to do the same thing. So we have a remainder of negative 4. So we're going to write it as plus a negative 4 over the divisor, which is x minus 3. So like that, or if you want to rewrite this part instead of plus and negative, just as subtraction. So 6x plus 5 minus 4 over x minus 3. That would work too. All right, so that's what it would look like if you get a remainder. You end up with a last term where it's the remainder over the divisor. So technically this expression isn't a polynomial anymore because it's got this thing on the end that's not a monomial. But that's okay, right? I mean, if you get a remainder, that's just what happens. So there's nothing wrong with having that happen whatsoever. It just means that the division that you're doing, it doesn't divide evenly because you're not getting a remainder of 0. So the fact that you end up with a thing that's not really a polynomial at the end, where the quotient's a polynomial, but then this remainder part's not. Totally fine. That's what's supposed to happen. Okay, next. This is the kind you got to watch out for. And why do you have to watch out here? Because there are terms that have coefficients of 0. Right? Look at the numerator here. We got an x to the 5th, 4th, 3rd squared, no x term, and then that constant of 8. And then in the bottom, there's also no x term, because you got an x squared, and then you got just a constant, right? Where's the x to the 1st? It's not in there. So when that happens, when there are missing terms, you got to add them in. Otherwise, your division gets all misaligned. So this is a thing that sometimes it's easy to forget to do it, but you would catch it right away because your division would look all messed up. Like in the first step, you'd be like, oh, this doesn't line up at all. And then you'd go, oh, yeah, I'm supposed to have like a 0x or a 0x cubed or something. But what I'm going to do to put those terms in there just so everything lines up properly, you could write x squared plus 2 as x squared plus 0x plus 2. Right? Then that x term is in there, right? Like it's that way it's written in so everything spaces out correctly, even though adding in 0x wouldn't change the value of the expression whatsoever. And then our dividend, so it should be 4x to the 5th minus 3x to the 4th plus 8x cubed minus 5x squared plus 0x plus 8. And for emphasis, actually, I was going to make those a different color, so let's see here. You gotta add these in, right? So just to emphasize them a little bit more, I'll make these kind of a maroon color on top of the blue. But that's what you would have to do here. And then once you've got those in there, you do it the way we've been doing it before. So like what would you have to multiply by x squared to get 4x to the 5th? Well, you'd need a 4 to get the right coefficient, and then you need an x cubed, since when you multiply that by x squared, that'll give you x to the 5th. So you'd have 4x to the 5th, I guess then plus 0x to the 4th, since 4 times 0 is 0, and then plus 8x cubed. And if you subtract, let's see, x to the 5ths are gone, x cubes are also going to be gone. You'll just end up with a negative 3x to the 4th, and then I guess plus 0x cubed minus 5x squared. And then we go again. So what do we have to multiply x squared by to get negative 3x to the 4th? Well, we'll need a negative 3 to multiply by that coefficient of 1 to get the negative 3 down here. And then we'll need an x squared. Since x squared times x squared, you can add the exponents to get the x to the 4th. So you'd have minus 3x to the 4th, then plus 0x cubed, since you're multiplying by 0, and then minus 6x squared when you multiply by 2, and then you subtract that row. Let's see, that's not going to be anything there. Neither is this, right? So you're going to have a 0x cubed, and then minus 5 plus 6 is 1, so plus x squared plus 0x. I guess in a way you could jump over this line, but it's probably better to write it in. Then in order to get a 0x cubed, you're going to need 0x. Right? You just need a coefficient of 0 to get that right. So, but if you're multiplying by 0x, you're just multiplying by 0. So you're getting a row of all 0 coefficients. Subtracting there, you'd have x squared plus 0x plus 8. And then what do we need to multiply x squared by to get another x squared? It's just 1. So plus 1, because 1 times x squared is x squared. And you get x squared plus 0x plus 2. And if we subtract that, we're going to end up with 6, right? From the 8 minus 2. That's all that's going to be left over. So then, let's see, what we're going to get for our solution. I guess I'm going to write it over here. It would be 4x cubed minus 3x squared. You don't really need to write in the 0x, so I'm just going to write in a plus 1. And then plus, for the remainder, 6 over x squared plus 2. Like that. And that should take care of that one. So the main thing here is just be careful when you have those terms that are missing effectively, which would just be the ones that have coefficients of 0 where you wouldn't write them in. You got to put those in, otherwise things will get kind of messed up. Your division won't align properly when you do the long division. All right, that's one way to do it. The other way, which you can't always do, but sometimes you can, is you can use something called synthetic division. And if you've never done this before, the reason why someone would want to do it differently, even though we have a perfectly good way of doing division already, is because synthetic division is shorter and it's really small when you write it out on the page. It's not like this, where it's half a page long. Basically, if you use synthetic division, it always ends up being like 2 inches tall. And you go, okay, that seems like an improvement. That's a lot smaller. All right, well, it is condensed or compressed. Yeah, it's compressed like this. So it's just not very tall. And it takes up less space. It tends to be faster, but you can only use it, like it says here, when the divisor is a binomial with degree 1 and leading coefficient 1. Otherwise, you can't use it. And so these are the steps here. This is easier to see with a specific example, which we'll get to in a second, but these are the things that we're going to do. And then this note down here is really just here to kind of emphasize this piece up here, where if you have a divisor that has a degree higher than 1, you can't do it. So like if you were going to divide this polynomial by x squared minus 3, you can't do synthetic division because the divisor's got degree 2. And then this one, the divisor has a leading coefficient that's not 1, right? It's got a leading coefficient of 4 because of that 4x, even though it's got the right degree. So it's got to be degree 1, leading coefficient of 1. But if you've got that, then look how much less space I left here, even though this looks pretty big. So what does this look like? Well, there are a couple different ways to draw it. I basically draw it like this, where I make kind of a division symbol but bigger and upside down. And then and if I go by the steps, the first thing is write the dividend with coefficients. So here's your dividend, this long polynomial right here. So the first coefficient's a 5 for the 5x to the 4th. Then you have a 31x cubed, so I'd have a 31. Then a negative x squared, so that's a negative 1 for the coefficient there. Negative 46x, that's a negative 46. So whenever you're subtracting, that minus sign always goes with that coefficient, right? So negative 1, negative 46, and then negative 23. All right, then you replace the divisor with the root of the divisor. So if you just want to think of it as it's the number that if you put it in for x, that would make your divisor 0. So here that's negative 6, and I would put that out here. Then what you do, I'm just going to scroll down for the rest of it. The first thing is you bring down the first coefficient. So the first thing is that 5, you just bring it straight down, and then you'd have a 5 down there. And that is what it says up here, right? Bring down the leading coefficient. Then what you do, and then this would be step 4, is you multiply this negative 6 out here by 5 and put the result right there. So negative 6 times 5 is negative 30, and that's where it goes, right? So basically, I guess I can draw another red arrow. You're going like that, right? So it's negative 6 times 5 ends up there, negative 30. Then if you add down, this is the part that throws people off. If you're not used to synthetic division, this is the thing that's weird, because when you do long division, you're always subtracting, right? Like if I go back up just to point at it, right? You do the multiplication, then you subtract, right? You subtract, 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 subtract. Here, you add, right? And that's the part where if you're not used to it, it feels weird, right? Because you're used to doing long division where it's always you subtract what's underneath, but here you add it. And that feels like it's backwards. But after you do a few of these, it'll start to make sense and it'll start to feel natural. So 31 plus negative 30, or just 31 minus 30, that's 1. All right, and then you keep doing the same process. So negative 6 times 1 is negative 6. You add down that column, that's negative 7. Then negative 6 times negative 7 is positive 42, so that goes there. Add down the column, that's a negative 4. And then negative 6 times negative 4 is positive 24. And so what we're going to end up with, it looks like, is a 1 right there. Okay, and I guess I can put the other red arrows in, since we are doing the same procedure over and over. Right, I guess we'd have red arrows going like this. Right, since, for example, the -6 times -7 is how we're getting that 42. Okay, so what polynomial is that? Because that's not really written as a final answer right now. It's just written with a bunch of coefficients. Well, the degree of the polynomial that you end up with should be 1 less than your dividend, because the degree you end up with should always just be basically what you would get if you subtracted the 2 degrees of the polynomials that you're dividing. So you have a degree 4 and you're dividing by a degree 1, you're going to end up with a degree 3. So like the solution here, it's going to be 5x cubed, right? So there it is, 1 less than the degree here. And it's because we're dividing by something of degree 1, so effectively we're subtracting 1 out of the degree. Plus 1x squared is plus x squared, then minus 7x minus 4, and then we had a remainder of 1, so that would be plus 1 over the real original divisor of x plus 6. And that is the final answer. There is one other thing I wanted to point out about how when you divide what your leading what your degree is, not your leading coefficient, like up here, polynomial on top, degree 5, on the bottom it's degree 2, the answer degree 3, right? So it's like you could subtract 5 minus 2 and get 3. And then here, degree 4 divided by degree 1, 4 minus 1 is 3. So that is the way that it works. So then that means that what we get in number 8 is also going to be degree 3, because we're dividing a degree 4 by a degree 1. But if we were going to do synthetic division here, you'd replace the x minus 2 with just 2, right? Because if x was 2, that would make this 0. So I'd have a 2 out here, like where I had the -6 in the last one. I can scroll up to get both of these on the screen at once. Then I'm going to make the division sign upside down. And then notice I've got some 0 coefficients here, because this is going from x to the 4th to x to the 1st. So I'm going to have a 1 for the x to the 4th, and then a 0 for the x cubed, and another 0 for the x squared, then a minus 2 for the minus 2x, and then a minus 12. Right? So then, let's see, once again, make those maroon. Right? You got to put these in here to account for those missing terms, or those missing powers of x. And then from there, we're going to do what we did before. We're going to take that 1 and bring it down. That's the first step, right? So you do that, you get the 1 down there. Then 2 times 1 is 2. Add down the column, you get 2, right? And 2 times 2 is 4. You add down that column, 0 plus 4 is 4. Then 2 times 4 is 8. Then if you add down that column, it's 6. Then 2 times 6 is 12. You add down that column, 0. Great, we got a remainder of 0. So I guess I can draw in those red diagonal arrows again, right? Because we were kind of going like that, like that, and like that, and like that. All right, so to go back and write out our solution, it looks like what we're going to get for our solution. So remember, it's going to start 1 degree below what we're at here. So it's going to be 1x cubed, or just x cubed, then plus 2x squared, then plus 4x, and then plus 6. And that's it. So that 0 in that last spot, that just means the remainder is 0. And if you have a remainder of 0, you don't write it in, right? When you divide 9, or I'm saying this backwards, when you divide 72 by 9, you don't say it's 8 with a remainder of 0. You say it's just 8, right? And that's kind of what we're doing here, except that's with a polynomial. All right, then there are a couple of theorems that are at the end of this section. These aren't really big things, but they show up once in a while. So they kind of come in handy every once in a great while. I guess that's what I'm saying. So this remainder theorem, if you wanted to get the remainder really quick of dividing a polynomial by something of the form x minus c, so degree 1, leading coefficient 1, then the remainder is just f of c. And when might you want this? Well, maybe if you were trying to factor a giant polynomial and break it down into smaller, more digestible pieces, because then if you can figure out the remainder really quick, then you could figure out if the remainder is 0 really quick, right? Because then if it is, then that's a factor, right? So maybe something like that, you could use it to do that, which would be something we're going to do like pretty shortly, actually. So we want to see the remainder when you divide by x plus 1 of this thing. All right. So x minus c here, the thing that we're dividing by, it's x plus 1. But to write it more in this format where it has a minus, I'm going to rewrite this as x minus negative 1. All right, that's the same thing as x plus 1. So then that means that c is negative 1. And so then that means what we need to do is find f of negative 1. Right, that'll give us the remainder. So f of negative 1 is going to be negative 1 cubed plus 3 times negative 1 squared plus 5 times negative 1 and then minus 4. So negative 1 cubed is negative 1, and then negative 1 squared is 1, so 3 times 1. And I guess I'll leave the rest of the multiplication alone for now and just do it all in the next step, because all we have left is addition, subtraction, and then a couple of multiplications, so we can do the multiplications now. 3 times 1 is 3, and then 5 times negative 1 is negative 5, and then minus 4. So then, let's see, negative 1 plus 3, that's a 2. So 2 plus negative 5 minus 4. 2 plus negative 5 is negative 3. So negative 3 minus 4, which is negative 7. So what does that tell you? That's the remainder, right? So then negative 7 is the remainder. I guess the remainder when you divide by x plus 1, right? So it doesn't divide evenly, because if it did, you'd get a remainder of 0. And speaking of which, that's what the factor theorem is. So these are written like they're separate things in our book, but let's see, I can get these up here on the same screen at once. They're not. Really, the factor theorem is a special case of the remainder theorem. These are really the same thing. It's just the factor theorem is more specific and the remainder theorem is more general, but they're the same idea. So if f of c is 0, then x minus c is a factor. Sure, because f of c gives you the remainder. If you're getting a remainder of 0, then that means that it divides evenly, which by definition would mean that it's a factor. So yeah, it comes directly out of the remainder theorem. It's a direct consequence. So then what we can do is you can say, okay, well then if we knew that f of c was 0, we could go, oh, then x minus c is a factor, so we could break down the giant polynomial into a product of smaller polynomials. So we're just going to see if we can do that. So first we want to see if x minus 3 is a factor of f of x. And if it is, then we're going to factor f of x and write it with 2 little polynomials instead of 1 big polynomial. All right, so then what we're trying to do, I suppose, is then we're going to say, well, then x minus c, just to kind of go along with how it's defined up here toward the top. Here, that's x minus 3. That's weird. I can't write all of a sudden. There we go. X minus c is x minus 3. So that means that c is 3. And what we're going to have to do is we're going to have to find f of 3. Okay. Well, then f of 3, if we substitute in, it'll be 2 times 3 cubed plus 5 times 3 squared minus 11 times 3 plus 4. All right, well, 3 cubed is 27. And then 3 squared is 9. All right, well, it doesn't quite look like this is going to work. We're going to get a lot more positives than negatives out of this, because we're going to end up with 54 plus 45 minus 33 plus 4. And even if you don't see what that is right away, it's pretty clearly not 0, right? If you just look at which ones are positives and which ones are negatives, like these two are going to overwhelm that negative 33, right? So yeah, I mean, you're going to get 99 minus 33 plus 4, which is 66 plus 4, which is 70, which isn't 0, right? So you'd say, well, 70 is not 0. So x minus 3 is not a factor of f of x. All right, so that one's not. And since it's the same polynomial here in 10b, you can probably guess that 10b is, and that is true. It does work. So I just wanted to go through what it looks like when it actually works, because you do have an extra step at the end there. But our x minus c here, the thing that we're going to divide by is x plus 4. So that's x plus 4, which to write it in this format with subtraction would be x minus a negative 4. So that would mean that c here is negative 4. And what we want to do is find f of negative 4. So we already kind of know, right? We already have the spoiler that this one should be a factor. So that means f of negative 4 should work out to be 0. So let's see. If it doesn't, then I guess that would mean that I messed up. So 2 times negative 4 cubed plus 5 times negative 4 squared minus 11 times negative 4, and then plus 4. Okay, powers. Negative 4 to the third is negative 64. So you have 2 times negative 64 plus 5 times negative 4 squared, that's 16. And then minus 11 times negative 4, and then plus 4. All right, and then doing all the multiplication. Let's see, we're going to have negative 128 plus 80. That's what 5 times 16 is. Minus negative 44, and then plus 4. So let's see, negative 128 plus 80 is negative 48. And then that's going to be plus 44 plus 4. Yeah, that works, right? Like you can see it now. That's going to be negative 48 plus 48. So that is 0. Okay, good. Because since we're getting the 0, that means that x plus 4 is a factor. All right, well then more specifically, and I need more room than what's underneath, I think. So what I'm going to do, I'm going to make a big box over here, and I'm going to do it over on this side. Because then we're actually supposed to do the division. I guess since I'm kind of running out of space, I should use synthetic division because that's nice and small. And I can because we're dividing by x plus 4. That's degree 1 leading coefficient 1. So if you're going to use synthetic division, it's going to look like this. Right? So negative 4, and then writing out f of x with coefficients, you have 2, 5, negative 11, and then 4. Right? And then you'd bring down the 2. And then negative 4 times 2 is negative 8. Add down, that's negative 3. Negative 4 times negative 3 is 12. Add down, that's 1. Negative 4 times 1 is negative 4. Add down, that's 0. Okay, well, we knew we should get a remainder of 0 since it divides evenly. We already know it's a factor. So then what does that mean? Well, then that means that our quotient ends up being, so just with the 2, negative 3, and 1 down here, it's going to be 2x squared, right? 1 degree down from the original, since we're dividing by a polynomial of degree 1, minus 3x, and then plus 1. So that means that f of x could be written as x plus 4 times 2x squared minus 3x plus 1. There. So now it's written in factored form, although, and I did this on purpose to kind of foreshadow what we're going to do in the near future, 2x squared minus 3x plus 1 actually factors. We're not quite there yet. That's the kind of thing we're going to do in section 4.5. But, I mean, for this section, this would be as far as you have to go. So the part in brown is just for the near future. But 2x squared minus 3x plus 1 actually factors into 2x minus 1 times x minus 1. Right? And then that's something you couldn't factor any further than it is. but I figured that foreshadowing there was worth it because it's in the very near future that we're going to talk about that stuff. But that should cover 4.3, I believe. And honestly, the biggest stuff is what happens earlier in this section. So like the long division and the synthetic division. But then these formulas, right, like or these theorems, like the factor theorem, then up here the remainder theorem, they do come in handy every once in a while, so they're worth going over.